Welcome you all back to our seminar series through the NHS Southern California Environmental Health Sciences Center. We are starting, this is the kickoff, starting our new academic year. We typically have seminars of interesting speakers on assorted topics from September till June. The first Friday of the month. We invite you to check out and be aware of that. Maybe set that time aside for on your calendars. We're starting off the seminar seasons, I guess, in virtual mode, which may be where we are all year long. We'll have to wait and see. But we are happy to, thrilled to have George Ban-Weiss with us today to talk to us about some of the issues in climate change and what he's been doing in that venue. George, for those of you who don't know him, is a professor at Viterbi and has been at USC now for several years, is an accomplished modeler. He's thought a lot about air quality, climate change, and not only understanding it, but what we do about it and sort of what mitigation, what adaptation strategies are really going to be useful in trying to accommodate the changing climate that we find ourselves in. And I could speak for quite an expanded time about all of George's accomplishments, his awards, his day life as a research engineer faculty, his nightlife as an award-winning jazz musician. But I will just defer to George and let him tell you about climate change today. So George, thank you. Please go on.
Okay, thanks Ed so much for the introduction, and it's my pleasure to be here virtually today. Maybe I don't know if the video is visible, but maybe I'll turn it on just to show my face for a minute, or I don't even see my face, which is a great thing. So I'll turn it on for a second in case you can see it, just to say hello, and then I might turn it off so I can pace around my room here as I'm talking. But anyway, it's my pleasure to be here. I'm going to talk today about the work that my research group has been doing at USC for the past 7 years or so. I started in 2013, so just switched from assistant to associate professor just in March. So this is my first talk as an associate professor. I had to change the title slide, which is exciting to have to do. Oh, okay, there we go. So maybe I'll stop my video and then I'll just pace around. Okay, so this slide shows the system that my group investigates. We look at climate, land cover, and air quality and their interactions. As many of you know, climate and meteorology can have an important effect on air quality. Air quality has an effect on climate. A lot of the work that I do is related to land cover, especially in urban areas, but sometimes non-urban areas as well. And land cover properties can have important impacts on climate as well, and can also have important impacts on air quality. So my group really investigates the synergies among these three different systems. As much as possible, we like to use computational models, ground measurements, and satellite observations together, and studies ranging from really neighborhood scale to global scale, depending on the research questions we're looking at. And I also really like taking systems approaches whenever possible to understand the environmental benefits and penalties of different solutions to environmental problems. Okay, so many of you probably have heard of the urban heat island effect, but just in case you haven't, the urban heat island effect describes a phenomenon where cities are usually warmer than rural surroundings. It's not always the case, but usually the case. The urban heat island effect is caused by the process of urbanization, and I'm going to talk more about that in a moment. The way that the urban heat island effect evolves diurnally varies by city. Some areas have larger urban heat island effect during the day. Some have a larger urban heat island effect at night. And I'm going to talk about urban heat islands in Los Angeles in this talk. Layering on top of the urban heat island effect is the fact that Los Angeles is projected to warm over the next century due to global climate change, the local impacts of global climate change. So you have these two impacts layering on top of each other. One is the global signal that has local impacts. The other is the local signal due to land cover change that, of course, has local impacts as well. This figure comes from some projections that were done by Alex Hall's group at UCLA. They're showing here the increases in extreme heat days per year that are expected by mid-century relative to today. And you can see many parts of LA experiencing roughly 3 times as many extreme heat days per year. Interesting to think about the discrepancies in the absolute number of extreme heat days on the west side of the basin versus the east side of the basin, where you have, places like Compton that are on the west side going from 1 to 3 extreme heat days per year. But of course, people in Compton are less ready for this increase. Even though the absolute number is lower, they're less likely to have air conditioning, maybe less likely to be able to afford air conditioning compared to some areas on the east side of the basin where their absolute numbers are very high, but are in many ways more prepared for that increase. So why am I interested in looking into local solutions for dealing with climate change? Well, I guess you could say that I'm somewhat pessimistic with respect to future policies that will reduce greenhouse gas emissions globally. To be able to mitigate climate change, we need those global scale decreases in greenhouse gas emissions, right? And that's, I would say, the top priority for sure. Given the lack of progress thus far, though, cities need local solutions to deal with the local impacts of climate change. And I would add, while synergistically reducing air pollution too, right? So if we have local solutions that are going to affect climate, those are going to have subsequent impacts on climate on air pollution as well. The figures at the bottom just make the point. This comes from a paper that was led by Steve Davis, who's at Irvine now. That, can you see my cursor? I think you probably can.
Yes, we can see it.
Yes.
You can see it. Awesome. Thank you. So this is showing a couple different future climate projections. These are emissions scenarios, so CO2 emissions per year. And these are old families of scenarios that the IPCC used, but this orange line is sort of a business as usual. The blue line is a hypothetical scenario where you flatten CO2 emissions, right? And of course, because of the dynamics of the carbon cycle, flattening CO2 emissions, even though that's hard to do, doesn't flatten CO2 concentrations, of course, right? So we still get increases by mid-century up to almost 550 ppm, which leads to almost 2 degrees Celsius warming by mid-century as well. So even this really challenging hypothetical scenario still leads to pretty large increases in CO2 and temperature increase. And so again, just motivating the need for local solutions to deal with climate change. So let's get into a little bit more detail on the urban heat island effect, and you'll see why. I'm going to explain this in a minute. So what causes the urban heat island effect? It is caused by the process of urbanization, essentially, replacing natural vegetative surfaces with human-made materials. Those human-made materials are generally dark. We refer to them as having low albedo, so they absorb the vast majority of incoming sunlight, and they heat up in the sun. Those materials are also thermally massive, so they absorb the heat and they retain the heat because of the heat capacity. Generally, urban areas lack vegetation relative to natural, to unurbanized regions, and vegetation acts as a natural air conditioner, right, through evaporative cooling. And so through urbanization that gets reduced. There's also anthropogenic heating, which is basically the waste heat that's emitted by air conditioners and engines. And there's some details with respect to the morphology of urban canyons that lead to shortwave solar radiation being trapped in the canyon, and also the long wave radiation escaping less efficiently. And so that can lead to some warming as well. Roughly speaking, a good rule of thumb for the composition of a city is that they're about 1/3 pavements, about 1/3 vegetation, and about 1/3 roofs and other things. So what can we do locally then to reduce temperatures in cities? And you can think of this as urban heat island mitigation. You can think of it as climate change adaptation. It's all different names for basically the same thing, which is reducing temperatures in a city, right? So what we can do locally that actually has impacts locally, right, as opposed to greenhouse gas emission reductions, right? It's critical to do that, but what we do locally doesn't really affect our climate locally, right? And so with urban heat island mitigation, what we do locally does affect our climate locally. So essentially what we can do is reverse the causal factors of urban heat islands, right? So that means deploying materials that, instead of being super absorptive, are reflective. Or we can deploy more vegetation, or we can reduce anthropogenic heat. So the first type of solar reflective material that is actually being deployed in a pretty wide scale way these days is cool roofs. On commercial buildings with essentially flat roofs, they look like this. They're white roofs, so they're very reflective. We don't see them from the sun, so we don't from the sun. We don't see them from the ground, so it doesn't really matter to us how they look. And then there are also cool roofs that can use standard materials that are used on residential buildings, like shingles, and they can be designed so that they look basically normal, but they increase more sunlight reflection. So they do that by mimicking the way plants work. They basically reflect near infrared light, but their reflectance in the visible part of the spectrum is pretty similar to standard roofing materials. And there are policies already that require the use of cool roofs. So those are being deployed in California in a fairly widespread way. Cool pavements are another opportunity. And you know, pavements in general, as you know, asphalt pavement has very low albedo. It absorbs, you know, roughly 90% of the incoming sunlight. And so many are considering the use of cool pavements. They're not as far along from a research perspective. They have potentially benefits, but they also have some penalties, and I'll get more into those details a little bit later. And so as of now, there are some pilot programs where they've been installed and around LA actually, and we're doing some measurements to see what the impacts of those installations are. But I'd say the jury is still out on cool pavements as to whether their benefits outweigh their penalties. Cool walls are another example. We've done a few studies on cool walls recently, and I'll talk about those in a little bit. Those are not really as far along as cool roofs either. Vegetative roofs can help. They don't necessarily make sense in climates where you don't get a ton of precipitation, right? So if you have to irrigate a vegetative roof to get a cooling effect and to keep vegetation alive, you know, you end up having water use issues around that. And then street level vegetation, like street trees, are a really important aspect to consider, because they not only increase evaporative cooling, but they also provide shade, which is one of the most important things to do if you're trying to make people more comfortable outdoors. So some of the questions that are important to address here are: which measures should be prioritized? What are their benefits and their penalties on, you know, environmental systems that are beyond what they're intended for, right? So one of the things I'm going to look at is, how do cool roofs affect air pollution, right? That's not their intent to affect air pollution, but they do. And then what are our desired outcomes? Why are we installing these in the first place, right? Are we trying to reduce air temperature? Are we trying to reduce surface temperature? Are we trying to improve thermal comfort of pedestrians? Your decisions on which measure should be prioritized ultimately depends on what the desired outcome is. And so it's important to define those. And I've noticed that sometimes in the policy world, they're not super clear in defining them. So I'm going to talk quite a bit about particulate matter. I don't really have to talk to this crew about the importance of studying particulate matter. It has important health impacts and is also a climate forcing agent. If you look at radiative forcing from various climate forcing agents, you know, aerosols are an important one. There's still a fair bit of uncertainty on their magnitude, both in terms of direct effects where they interact with solar radiation, and also their indirect effects where they affect cloud distributions. And so that's those are topics that my group also works on, but I'm not going to talk much about that today. And then one more thing I'll talk about a bit at the end, if there's time, is the impacts of adopting drought tolerant vegetation. So that's in the realm of, you know, changing land cover and its impact on climate. The intent is to reduce water use, of course, but it has sort of unintended consequences on climate, which we had hypothesized were going to be negative, although in the net they turned out to be positive, which was quite interesting. And so, you know, we have policies and programs that encourage converting grass to drought tolerant vegetation. And so I'll talk a little bit about that study as well. So just some research questions that I'm going to address in this presentation today, some examples. So how has historical urbanization impacted the climate and air quality of Southern California? That helps us understand the urban heat island effect in LA. To what extent could heat mitigation strategies mitigate the urban heat island effect in LA? To what extent could heat mitigation strategies counter future climate change in LA? So it's basically comparing the magnitude of temperature reductions from urban heat island mitigation to future climate change. How could these heat mitigation strategies affect air pollution? What are, I probably will skip over this, but there were a few, well, there was one study in particular that suggested that deploying cool roofs could lead to global warming, and a couple studies that claimed that cool roofs could lead to global cooling. And so we did a study to see who was right and try to add to that debate. And then what are the climate consequences of replacing lawns with drought tolerant vegetation? And then I'll spend a little time at the end talking about work that we're doing right now that is changing directions a little bit from this topic, just in case it helps frame future discussions on collaborations and things like that. Okay, coffee sip break. Okay, so the first thing that I will talk about, which is one of the first topics that we tackled when I started at USC, was how has historical urbanization affected climate and air quality of Southern California? The reason to look into this is that usually urban heat islands are defined by comparing the temperature in a city relative to the temperature outside the city, right? So, but in LA, that's really hard to do because there is no rural temperature outside the city, right? It's either ocean or it's mountainous, and there isn't a sort of good rural reference point. It's all urban. And so we decided to tackle it by sort of flipping our approach of quantifying this on its head and saying, well, let's do some model simulations where we compare climate in Los Angeles as it is now to our sort of best guess at what it was prior to any urbanization. Because after all, the urban versus rural way of defining urban heat islands is really just using the rural area outside the city as a proxy for what the area was prior to urbanization. So the first thing we had to do was to take a community climate model known as WRF and update it so that we could use it to address the research questions that we were interested in. There were several things about the way that WRF parameterized urban areas that were really unrealistic and essentially made it impossible to use for what we were wanting to use it for. And so that was one of the first studies that my group did, was to update the model. And so not only did it allow us, so essentially what we did is updated the model so we can account for high resolution heterogeneity and land surface properties within a city. And we did that using satellite observations. It enabled us to do basically all the follow-up studies, but also happened to improve model biases relative to observations by 50% as well. So it was ended up being worthwhile. This gives, well, the top row shows the satellite imagery that ended up being used as an input to the climate model. So we're accounting for the heterogeneity in green vegetation fraction, leaf area index, and albedo. And so in this study where we investigated the urban heat island effect, we compared the climate as it is now relative to our best guess at what land cover distributions looked like before urbanization, and I'll skip over the details of how we came up with that. But what we ended up finding was this. So this map here shows modeled air temperature change. So it's basically comparing LA as it is now to LA pre-urbanization. The left is showing during the afternoon and the right is showing at nighttime. And so it's showing change in 2-meter air temperature. And so you can see that on the left-hand side, if you take the spatial average of the urban area, you get that urbanization or the urban heat island effect in the daytime is about 1.3 degrees C. And at nighttime, it's 3.1 degrees C. So you can see the magnitude of the urban heat island is larger at night, which is pretty expected given the high heat capacity of human-made surfaces. Now, urbanization itself has affected temperature, but also affects wind speeds through changes in not only the land-sea contrast, which drives the magnitude of the sea breeze, but also the surface roughness. So the surface roughness in LA basically impacts the amount of friction that air encounters, right? And so through urbanization, we've increased surface roughness in LA, and so that's reduced the mean wind speed in LA, and that's had subsequent impacts on air pollution concentrations. And then also is a feedback into temperature change as well, because you get less of the onshore flow. And so the point here is that, you know, it's not just temperature changes we need to worry about, it's also wind speed changes. And that sort of prompted us to want to investigate then what the air pollution impacts of urbanization are. And that's assuming that emissions are held constant, right? So the process of urbanization and changing land cover just itself affects air pollution, even when emissions are assumed to be the same. And so that is what we did in a follow-up study, really to highlight the importance of taking the heterogeneity in land cover into account when you're doing air pollution simulations at, you know, the scale of, even at the scale of, you know, all of Southern California. When we updated the land surface model in these simulations, it had big impacts on air pollution, both ozone and PM2.5 in various species. And so this entire paper was on that, right? And I'm going to talk more about land cover impacts on air pollution later. So I'm just going to, this slide was just intended to sort of bring up the point that land cover change itself affects air pollution, even assuming that emissions are constant. And I'll get more into that in a minute. Okay, so now I'm going to start talking about heat mitigation strategies, right? So far we've talked about urbanization and the heat island effect. Now we talk about heat island mitigation. And so I'm going to start by focusing on cool roofs and a little bit on cool walls. And the question is, to what extent could deployment of these materials mitigate the urban heat island, essentially reduce temperatures? And so to start, to understand how big of an impact cool roofs can have, we need to understand, well, what's the reflectivity of roofs now, right? If all roofs have high reflectivity in their baseline, then there isn't much room for improvement. And starting about 7 years ago or so, we tried to tackle that question by using aerial imagery. So up until then, there had been some measurements on rooftops with, handheld instruments, but you can only do so many measurements like that, especially because it's really hard even just to get access to rooftops to make these measurements due to, I think a lot of the building owners are worried that someone will fall off a roof and sue them or something like that. And then on the flip side, using satellite data is generally too coarse. You can't see a roof from satellite data. The spatial resolution isn't good enough. So what we did is we got aerial imagery and use that imagery to essentially applied algorithms that are used in the remote sensing albedo products. So Modis has a product for getting albedo, and a couple other satellites do too. And so we repurposed that approach using for this aerial imagery, which I won't go into the details, but we got imagery that was actually real radiance data. It was better than just photos that looked good. So it was actually scientific data. And so what we ended up doing was we were able to look at individual rooftops for the entire city of LA and actually 6 other cities in California and determine the albedo of every single rooftop, which was helpful because we could then have a good sense of the average albedo of roofs that are out there, which ended up being 0.17. That's this value here, right? So that means that 17% of sunlight is reflected, which means the vast majority is absorbed, right? Which means that there's a lot of room for improvement. So this is for LA. This is looking at all 1.1 million roofs in LA. And so, but we made a second point as well, which is that if you look at the distribution of roof area, you realize that the vast majority of rooftops in cities are residential rooftops. They're not the big kind of commercial buildings. And up until that point, there were only cool roof policies for commercial buildings, not for residential homes. And so we made the point, and there's good reason for that. That was because initially cool roofs were used for energy efficiency, not for urban heat island mitigation. But anyway, we made the point that if the goal is to reduce temperatures, you need to focus on the roofs that are making up most roof area, which is the smaller residential homes. And so that is, I think, shown here. Most roofs have low albedo, and so they therefore absorb the vast majority of sunlight. Most roof area was comprised of residential homes, and so we need to go beyond the past requirements, focusing on commercial buildings. There was a really cool workshop that was put on by this organization in LA called Climate Resolve, where they brought together a large handful of researchers to present their work with policymakers that were in the mayor's office. This was back, I guess in 2013 or 2014, probably 2013. And so I presented these results, and there were a bunch of other researchers there as well. And what ended up coming of it was a regulation where the city itself became the first major city to require that residential homes need to use cool roofs when they're going to put a new roof on their home anyway. So that was interesting policy, and other cities have followed suit as well. So if we look now at the climate impacts of adopting cool roofs, these maps show temperature change from adopting cool roofs, hypothetical scenarios where you basically adopt cool roofs on every building in the whole city. And the figure on the right shows what if we adopt cool roofs on commercial buildings. Again, those commercial buildings they can be white roofs, right? They can be very reflective. So what you see is big temperature impacts in the areas where you have a higher density of commercial buildings, right? Which is not everywhere. So you get these smaller regions, but with pretty large temperature reductions. If you deploy cool roofs just on residential buildings, we assume that those residential buildings aren't going to get the white roofs. They're going to have the lower reflectivity roofs. They're still cool roofs. They're more reflective than standard ones, but not as reflective as commercial buildings. And you see, since the most rooftops in the city are residential homes, the spatial coverage of the cooling effect is much larger, but the magnitude isn't as high in any particular location. And then this puts them both together in a simulation to sort of test the linearity of the effects. And so what we found is that residential cool roofs were responsible for about 2/3 of urban cooling, which sort of bolstered what we had said before without having the temperature impacts piece. And daytime cooling was larger than nighttime cooling. We more recently have done some simulations looking at cool walls. So this is making vertical surfaces reflective, and it was kind of an interesting study just from a scientific point of view, because these are surfaces that are vertical instead of horizontal. We added some new parameterizations to the model to better account for the temperature in the urban canyon. The older version wasn't quite as good at that. And so saw some interesting differences between cool roofs and cool walls. And this map shows the afternoon and the evening change in canyon air temperature from deploying cool walls. And you can see, cooling effects that are up to about roughly 0.5 degrees C, or a little bit higher. And you can also see the effect accumulating as you move to the east, right? Because you have that onshore flow, and so the cooling effect accumulates as the winds blow inland. I'll talk just for a second about cool pavements. So cool pavements are, I would say in the testing phase now. We did a study several years ago that was collaborating with LBL and UC Davis, where we looked at various aspects of cool pavements. What my group was looking at was the climate impacts. This photo on the left shows a cool pavement. It doesn't have to look like this. The design of this particular product was to try to make this parking lot look like a park, like AstroTurf or something like that. But these are two other examples of what cool pavements can look like. They can look reflective like this, or they can be less reflective and reflect light outside the visible part of the spectrum. And so we did some modeling to look at the cooling effects if we deploy these cool pavements in cities across California. And what we can see is cooling effects that are up to roughly 0.5 degree C, or a little higher in cities around California. What I want to actually, I'll show this first. So everything I've presented so far is related to cooling effects is modeling, right? And we did a study a few years ago as well that was trying to use observations to detect whether the heat mitigation strategies that have been installed so far, which is basically cool roofs, right, which have been deployed starting in the mid 2000s, at least for commercial buildings, for those energy efficiency standards I talked about before. So we had a project where we did mobile transects. So we basically have this temperature sensor that's designed to accurately measure air temperature outdoors, put it on a car and drove around some different neighborhoods. Also had some high density weather station data, and had a couple regions of focus. And the idea was to see if we could detect temperature change impacts from deploying heat mitigation strategies. So we basically, you know, for the weather station perspective, we had a bunch of weather stations and then took the mean properties within 500 meters of each of those weather stations, looked at a lot of different properties, including cool roof deployment and albedo. And so what we ended up finding from this was what I think is the first observational evidence that cool roof deployment is associated with neighborhood scale cooling. So that was a interesting finding. The next set of slides puts into perspective the temperature reductions from cool roofs related to future climate change projections in LA. And so I have, I think, just one slide on that just to give you a sense. So the top row here is climate change under two different scenarios in mid-century. RCP 2.6 assumes extreme mitigation. RCP 8.5 is more like a business as usual scenario. And then top row is mid-century, bottom row is end of century. And so what this has is basically climate change plus cool roof deployment, right? So we can see what the net amount of warming is, what the residual warming is after climate change and with cool roof deployment. And so you can see in the top row that cool roofs reduce the average warming from 2 degrees to 1 degree C. So it has an impact. It doesn't fully reverse it, but it has a noticeable impact. But by the time you get to end of century, the residual warming that remains is a lot. And so what this tells us is that, you know, you can think from a climate change perspective, you can think of cool roofs as offsetting pretty significantly the local impacts of climate change in the next decades. But by the time you get to end of century, the temperature reductions are just overcome by climate change. And so, you know, the only way to achieve long-term, even regional climate stability is through global scale reductions in greenhouse gas emissions. This slide, so we also do some work more at the neighborhood scale. And so this is presenting some work that we did at, using a micrometeorological model, looking at different heat mitigation strategies on temperatures, but also pedestrian thermal comfort. And so here we were looking at adding green roofs, even though I don't think they're that smart in a place like LA, cool roofs, adding trees and cool pavements. And I wanted to include this just because I've talked a little bit about cool pavements, and there are some interesting issues with them. Cool pavements work by reflecting sunlight, right? And pavements are at the surface, unlike roofs, which are, you know, at the top of the canopy. And so what ends up happening is cool pavements lead to temperature reductions, but they also can increase the amount of solar absorption by pedestrians. And so it ends up being this tug of war where, you know, the cooling effect would tend to make people more comfortable, but the increased sunlight absorption effect would make them less comfortable. And so the question is, which one wins? And there's still a bit of a research debate about that as we speak. This study suggests that the solar absorption effect wins, and so that people would tend to be less comfortable with cool pavements. They still reduce temperature, but they aren't necessarily good for pedestrians that are really near the pavement during the day. What we found in this work, though, is that in the evening after the sun goes down, that solar absorption effect, of course, doesn't matter anymore. And so you get some residual cooling from cool pavements. And so, again, it all comes down to your objective, right? If your objective is to make people more comfortable in the evening when they're out on a walk or something, then cool pavements could be helpful. If you want to make them more comfortable during the day, maybe not. So, and then we also just highlighted the importance of shade, right? So adding trees had good improvements, of course, not just in air temperature, but also in this metric mean radiant temperature, which is indicative of thermal comfort. Okay, and then this was a article that was in the LA Times that my student Arash and I were in. I guess I'm just showing this to look really cool. Okay, let's move on to check the time. How could widespread deployment of cool roofs impact air pollution in LA? So this was a nice flow chart that was put together by my previous PhD student, Jia-Chen Zhang, who was a postdoc also for a while and is so just about to leave my group to go to a job. And this shows a flow chart of how increasing albedo in a city using cool walls or cool roofs can ultimately affect air pollution. So you get, as you increase albedo, you get decreases in temperature, you get decreases in wind speed, because in LA, it reduces the land-sea contrast, which slows down the sea breeze. Increasing albedo can also reduce the planetary boundary layer height. And so that, of course, affects air pollution concentrations as well. And, you know, decreasing boundary layer height can have increases in pollutant concentration. So there are these competing pathways. By increasing albedo, you can reduce ventilation in the basin, right? So reducing wind speed and reducing planetary boundary layer height, those both go toward decreasing ventilation and also dry deposition. By reducing temperature, you can, and then that reducing ventilation would tend to increase both ozone and PM, all pollutants really. By increasing or by decreasing temperature, you can increase gas to particle phase partitioning for semi-volatiles, and so that effect can increase particulate matter as well. But then on the flip side, decreasing temperature would tend to reduce temperature-dependent reactions and also temperature-dependent emissions like biogenic emissions, and so those effects would tend to reduce ozone and PM. So again, we've got this tug of war, and we're interested to see which one will win, and so that's where, you know, a model can really help. So there was a study, the first study we did on this was published in PNAS, and we were looking at how how Title 24, which is the policy that is at the state level, really focusing on commercial buildings for energy efficiency primarily, but then, you know, we have found the secondary effect of urban heat island mitigation, and looking at the effects on ozone and particulate matter. This figure shows how adopting cool roofs in Southern California could reduce the height of the planetary boundary layer. So this is showing change in annual average daily max planetary boundary layer height. And you can see that, you know, there are pretty important impact reductions in the planetary boundary layer height. We can put that in better perspective by not looking at just boundary layer height, but also integrating the wind speed effects as well. There's a metric called ventilation coefficient, which accounts for both of those at once. And so you can see that if you're looking at ventilation coefficient in percent units, that the annual average reduction in that coefficient is up to about 6%. And so then the question is, okay, how does that affect pollutant concentrations? I'm just going to focus on particulate matter here. Ozone, we ended up going into some more nitty-gritty in this paper about ozone because the impact depends on what your assumptions are for reflectivity in the ultraviolet part of the spectrum, because ultraviolet is what drives photochemistry. If you assume ultraviolet's the same, then you get reductions in ozone because of the temperature effects. But anyway, I'm not going to go too much into that. Instead, I'll just focus on particulate matter. And what you can see here is that the reductions in ventilation coefficient lead to increases in PM2.5 across the whole city or across the whole basin. And if you look at Mira Loma, which is the location with the highest measured PM2.5, you see annual average increases of about 0.2 micrograms per meter cubed. If you do an analysis, which essentially what you do is you take observations of PM2.5 and then you add the delta that we found here, right? You can then see, without worrying about model biases as much, you can see the effect on the number of days per year that LA exceeds the 24-hour PM2.5 standard. And you can see that it could increase those number of days by somewhere between 1/2 to 2. Non-integers can, because of the way we did a little bit of spatial averaging of the grid cells. And so, you know, this basically goes to show that those changes in PM2.5 could be important, even though they seem kind of small. Follow-up work by my PhD student, Jia Chen, started looking at the process drivers of those changes in particulate matter. So looking at how different species were affected, looking at the effects of ventilation, basically trying to understand the relative importance of these different pathways here. And so there was a whole study on that. And this shows some example. We also added cool walls to this study as well. And so this shows total PM2.5 reductions or increases, I guess change, I should say, in PM2.5. This is looking at nitrate as an example. And what we found is that the concentrations for primary particulate matter, like elemental carbon, are mostly dependent on ventilation, right? That's as you would expect. They're not affected by, you know, temperature dependent reaction rates or phase partitioning or things like that. Concentration of secondary species are less dependent on changes in ventilation. For example, nitrate is highly dependent on this gas to particle phase partitioning and thus ambient temperature. And so we see increases in nitrate here because of the temperature reductions from cool roofs and cool walls. What time is it? 12:35. I think, well, I'm going to speak just briefly about beyond urban areas. What are the climate consequences of cool roofs at larger spatial scales than urban, so urban, continental, and global scale? This table shows some previous studies that had been done on this topic. The first 4 studies are basically claiming that cool roofs that are deployed in urban areas can have global cooling effects. There was one study that claimed that cool roof deployment could actually warm global climate, and he said that it was because of the fact that reflective roofs, that the reflected sunlight can be absorbed by black carbon aerosols, and also there were some cloud feedbacks in the polar regions. And so we wanted to, you know, contribute to this debate. And I thought that, to be honest, I thought that neither claim was super believable. And so we did some climate modeling studies using a global climate model. And what we found is that implementing cool roofs can lead to a global cooling effect, but it's statistically insignificant. So it's really, really, really small. And we investigated these different pathways from the Jacobson study, like, for example, how do absorbing aerosols influence the effect of cool roofs? And we found that they can attenuate the effect, right? They can lower the effect of cool roofs because of the absorbing aerosols effect of, you know, absorbing reflected light, but they don't reverse the effect. They don't cause warming. Okay, and then the last topic I think for this talk is thinking about what are the climate consequences of replacing lawns with drought tolerant vegetation in Southern California. So I just show this again to, as a reminder that any changes you make to the land surface can affect climate. And of course that can make air quality impacted as well. And so, the goal of deploying drought tolerant vegetation is to lower water use, which is super important. But we were thinking, we had hypothesized that this could have important impacts on climate as well, right? Because if you are not irrigating the soil and the soil dries out, you're going to end up with less evaporative cooling, and you could end up with warming then. And so that could be sort of an unintended consequence of adopting drought tolerant vegetation. Now, what we didn't think through with that hypothesis is the fact that the signal at night might be completely different, and it turned out that it was. So what this figure shows here is the influence. So basically, hypothetically, assuming that we replace all lawn in Southern California with drought tolerant vegetation to sort of bound the effect, right? And we found that, as expected, during the day we end up with warming when you do that, and the warming signal was about it was up to about 2 degrees Celsius, and it's dominated by the fact that drought tolerant vegetation is irrigated less, and so the evaporative fluxes during the day are lower, and so you have less evaporative cooling. Changes in roughness length. So basically, right, drought tolerant vegetation is different in size than lawns are. And so you change the roughness length of the surface, and also leaf stomatal resistance. So that describes leaves you can think of leaves as having little valves in them that open and close and either, allow water to transpire or not. And so, the stomatal resistance, so basically the how open or closed those little valves are, depends on the type of vegetation. And so that played a small role too, but the evaporative fluxes were the main role. At night, things were a lot different though. So you can see at nighttime, everything's blue. So that's a cooling effect, right? And so how did this work? So basically at night, the turbulent fluxes are no longer that important, right? The evaporative flux, the sensible heat flux, they are really low, and so those aren't the main fluxes that determine temperature at the surface. Instead, what you have is two other fluxes that play the dominant role. One is the amount of long wave radiation that leaves the surface and essentially acts to cool the surface, either being absorbed by clouds in the atmosphere, or if it's not cloudy, that flux goes to space. So that's one, and then the other is the ground heat flux. So at night, the ground heat flux is the opposite direction as it is during the day. At night, the surface is cooler than the subsurface because you have this long wave heat flux that cools the surface. And so you have a ground heat flux that is upward, right? You carry heat from the subsurface to the surface. As you dry out the soil, you change the thermal properties of the soil. And so that ground heat flux changes, and you end up having a decrease in that upward ground heat flux at night. And so that means that the surface itself gets cooler. And in retrospect, maybe we should have expected that. That's similar to why, when you go to the desert, it can be really hot during the day and really cold at night. And so that's what we found here. And so you can see also that the nighttime signal is larger than the daytime, right? So in the net, you end up with cooling. So thought that was interesting. Now, just some other research, I guess to relay what my group does in case it helps foster future collaborations or whatever. So we do a lot of other more aerosol focused research, looking at both aerosol effects on climate, and then also we do some measurement work related to emission sources. So
the work that we do on aerosol climate interactions is both modeling, and we do some measurements related to the climate relevant optical properties of aerosols. And then emission rates, we've been tending to, it's not a huge part of my research portfolio, but we've done some studies that have started looking at non-mobile sources, basically. So as mobile sources get cleaner and cleaner, the other sources get more important. And so as an example, now we're just finishing a study where we did emissions measurements of commercial harbor craft in the port of LA. And then another project that I'm working on right now that's a collaboration with NREL is looking at air pollution co-benefits of future scenarios of renewable energy adoption. And so we're what we're doing is all modeling related. So we're starting with a really detailed source-oriented emissions inventory. NREL has done a lot of modeling to look at different scenarios for adopting renewable energy in the future, both for the power sector, for buildings, for transportation, and for the port. And so they've got complex models that try to simulate those futures. And then we use their outputs to alter our emissions inventory into the future, and then ultimately run a climate chemistry model to see what the resulting impacts are for air pollution concentrations. So that's ongoing. And one more that I'll talk about quickly is a study or a collection of studies that have been led by another PhD student that just graduated that was co-advised with another professor in my department. And for that, she's an energy expert. And so we sort of put our expertise together and worked on looking at how, ultimately our goal is to look at how climate change could affect residential or really building energy consumption in general. And so the work we've done so far, we got smart meter data for a couple 100,000 homes across the SCE territory, and got a bunch of high resolution weather data, and then started looking at trends. And so looked at, for example, the sensitivity of energy use to temperature, which can tell us something about, under future warming, how much more energy might we use for cooling. Another thing that we did as a side project that ended up being one of the more interesting pieces actually was to use those data we came up with a method to determine whether or not a home has air conditioning, and that allowed us to look at spatial patterns and the fraction of homes that have air conditioning. And then on that, we layered some socioeconomic data, poverty percentile index, and so we could look at things like trends in covariation in poverty and your likelihood of having air conditioning, and things like that. Okay, so everything I talked about was done by my PhD students and not me, so I of course have to thank them profusely. I think these two pictures mostly cover all the students, but I showed results from Trevor Krasowski, Arash Mohe, Mo Chen, Joseph Ko, Yoon Lee, Jia-Chen Zhang. Hannah Schlereth is the one that has done the commercial harborcraft study, so no results from her yet shown. Is that everybody? I think so. And then funding from NSF and Rose Hills and SCEHSC, Air Resources Board, Strategic Growth Council. And happy to take questions.
So thank you, George. That was a far-reaching, sobering, and actually very thoughtful look at some of the competing mechanisms. So it's not always as we first think it to be in terms of what might happen. There are a number of questions that came in on the chat, and I'm sure people have several questions as well. Maybe we'll start with some of the questions on the chat. Early on, when you were talking about cool roofs, a question came up about what impact, if any, solar panels, particularly on residential homes, and as well as commercial operations? Do solar panels play a role in any of this heating, either in a positive or negative way?
Yeah, that's a great question, and probably the most common question I get after this talk. I should just add something into the presentation about it. But that's a really good question. At first glance, you might think that solar panels might be bad from an urban heat island point of view because they look so dark. But with solar panels, it's a little trickier because you need to account for the fact that they're not as bad as they look because, you know, a fraction of the incoming sunlight is converted to electricity as well, right? And so let's say that you have a solar panel that's 25% efficient, right? That means that 25% of incoming sunlight goes to electricity, and then they're usually, you know, 5-ish% reflective. So that means that the electricity plus reflectivity piece, which is basically everything that doesn't turn into waste heat, would be something like 30%, right? And so that means that the absorptivity would be 70%. So that's what goes into waste heat. So that's roughly the same as a good cool roof on a residential home, right? So in a way, you know, a solar panel, or it's even beyond in a way, I would say in reality and in actuality, a solar panel on a residential home is as good as a cool roof. I mean, assuming that it's relatively efficient. Compared to a white roof on a commercial building, from a reflectivity point of view, it's not as good because on a commercial building that's super white, it can be, you know, at least initially, it can be 80 to 90% reflective, right? And so that's then only 10 to 20% of sunlight being absorbed and turning into waste heat. And so, you know, from an urban heat island point of view, a solar panel is not as good as a white roof. But of course, you have to take into account the, you know, the climate mitigation, the climate change mitigation potential of avoiding CO2 emissions from solar. In the paper, we talked about how you could think about solar on residential homes as climate mitigation and adaptation sort of at the same time, right? Because you end up making electricity, so avoiding CO2, so that's the mitigation side. You also, you know, if you compare it to a dark roof, you end up saving, you know, a little bit of electricity even just from that mechanism, right? Like less heat transferred into the building. And then you also have the adaptation piece, which is, you know, urban heat island mitigation. So that's a great question.
Thank you. We have a couple of questions from Esther Margolis on architecture relating to green space and the use of either drought tolerant vegetation or shade trees and how that affects you know, the use. And I don't know, Esther, if you want to just consolidate those into one connected question, or how
well, I add, thanks. They're not, I don't know if it's possible to, maybe. So I'll ask them both together just for efficiency. So George, thanks for the presentation, really interesting. I wanted to know in sort of terms of thinking about how important, how the amount of residential land use in LA and its potential impact on cooling for the city, which is not dissimilar for some other cities. What about tree canopy cover in private properties? And have you done any, like the roof study, have you done any kind of regional studies on if we were to maximize tree canopy on private property and especially residential property, what kind of benefits that might bring?
Yeah, that's a really good question. We haven't done that work yet. It's been sort of on the to-do list. I think the thing that we need to figure out that we're not sure how to do is how to bound the possible increase in tree cover from that. So with roofs, it's easy because you have, you know, GIS building data, and so you can really accurately, you know, predict how much roof area there is in each region, and then assume that, you know, as a starting point, that all buildings get cool roofs to bound the problem. It's harder, at least for us, to understand, you know, from any kind of practical perspective, like what are the reasonable areas that could get new trees? And so what's the sort of maximum potential for tree adoption? So we haven't done that yet. We've done a little bit of work just at the neighborhood scale where you can just, look at a map and do your best. I've got a project now looking at Fresno, and we're doing some micrometeorological modeling that's kind of similar to what I showed in the presentation. And for that, we're working with an organization that's called Tree Fresno that understands on the ground like what drives tree adoption in private or public spaces. And so by working with them, we're hoping to get a good sense of where we can put trees. And at that scale we can be very specific. We're literally telling the model like where is each tree going in a neighborhood. But at a larger scale, at the urban scale, I'm not totally sure how to do it, but happy to hear suggestions either now or offline if that's something that you do.
I'll send you an email about what I think are some potential ways of modeling that. And then the second question was just hopefully very quick. In your studies comparing kind of irrigated lawn removal and replacement with native vegetation, did you assume that the replacement vegetation was going to be a low ground cover that wouldn't actually create any shade on its own? Or did you model it saying, well, what if it was more of a, kind of native shrub cover or something else that actually created enough shade to maybe bring temperature down during the day at the ground surface?
Yeah, so we assumed that it wouldn't cast a significant shade. So things would certainly be different if lawns were replaced with ground cover that did create shade.
Thanks.
Okay, thank you.
Thank you.
Rima, do you want to grab a short question and sneak it in here?
Sure. Thank you, George, for a really cool talk. So I had a couple of questions, but I can email you if you don't get to them, I guess. But first was, have you thought about ammonium sulfates and secondary formation? Does it kind of, do the effects you see from cool roofs go with reducing ozone and reducing ammonium sulfates?
Yeah, that was, so in that study maybe I won't go back to it, but in the study that looked at the process drivers and the different species, we looked at basically all species that were modeled. And so we did also see effects on ammonium sulfate as well. But I just showed nitrate sort of as an example species, partly because it had really strong phase partitioning effects. So I was showing it as an example of a species that wasn't dominated as much by ventilation, but yeah, ammonium sulfate was also affected for sure.
That makes complete sense. And the only reason I ask is because I think it's really correlated with sort of the oil refinery emissions. So from a health perspective, it might be, very interesting. And do you mind if I sneak in another quick question?
Not at all.
The other one is on sort of these micrometeorological effects. And is your sense that, like, let's say with cooling, any kind of thermal convection effects of like wind mixing or stagnation, it seems like they're very negligible compared to sort of the sea land effects that you're looking at with wind speed overall. Is that right?
So you're asking how big of a role the turbulent fluxes play relative to like advection from the sea breeze?
Exactly, at like a very micro level, like, block group, street canyon level.
And from a temperature perspective or from a airplane perspective, or I guess both?
From a perspective due to thermal or temperature effects, like from wind mixing and kind of diluting pollutants, I guess, or building them up if it goes the other way.
Yeah, so that's a really interesting question, because another thing that you could see, would be, for example, if you deploy cool pavements at wide scale. Let's assume there isn't a bunch of traffic on the street, right? You would expect less just convection, and so less dispersion of pollutants in general near the surface. And you know, at the scale of the studies that we did on that modeled air pollution, right, where we're looking at more regional air pollution, the advection piece, the you know, sea breeze scale effect, had really more of an effect, and that's partly just because that's the scale of the modeling. Although the convection piece that you talked about is related to the boundary layer height too, which also played a role. If you're looking at the neighborhood scale, they're both really important. So, as an example, when you do the micrometeorological modeling, what you end up seeing is that you end up better accounting for all of the airflow through the canopy, like between buildings and stuff, than a regional model does, right? And so you end up being able to distinguish really well what's the difference between the temperature, let's say like above the roof versus the temperature near the ground, right? And one thing that we've seen so far is that cool roofs, at that scale, when you do the modeling, they reduce temperatures near the rooftop, but those temperature reductions don't necessarily mix down to the near ground level, right? And so that would completely depend. And so basically temperature reductions end up being not as big as you would expect near the surface, which is where people are. And so, you know, in the end, what we've done with the micrometeorological modeling is, I would say, more along the lines of case studies, right? You can't really, they're so computationally expensive. You can't do climatological like simulations where you're looking under a bunch of different, you know, meteorological conditions. So you basically look at one day, one neighborhood, right? Often an extreme heat day where it's pretty stagnant. And so maybe it's not shocking that the roof level temperature reduction doesn't vertically mix to the near surface. So I think, you know, that's one thing that I'm pretty interested to continue is look at that effect under different conditions, let's say where there's higher wind speed and some more turbulence and more vertical mixing. I think I might have an undergrad researcher do that this semester. So, and basically more generally trying to resolve, you know, the predictions from these different scales and models. So I don't know if that answered your question.
Yeah,
but...
no, thanks. That's very
Okay.
cool. I might reach out to you at some point, but yeah, thanks.
So
Okay.
thank you. We're out of time. I want to thank George. If we were in the one room, we'd